Okay. So for new folks that are joining us this quarter, I want to briefly cover the study's intended purpose before we dive into the meatier part of the agenda. So the interagency team for the GLRI framework will be identifying the range of anticipated future conditions on the Great Lakes. So we're looking at things like water levels, wave heights, and ice conditions. And we're looking at these under a set of climate warming scenarios. And we are leveraging proven models to do this forecasting and to advance our understanding of future Great Lakes conditions. To complement the range of conditions that the team is developing, we will also be producing design and planning guidance checklists to help support stakeholders that are implementing Great Lakes coastal restoration projects. And we anticipate that we will incorporate your input that you share. So we really want these to be usable products, and we'll cover that more later on in the presentation. And just as a reminder, we are funded through the Great Lakes Restoration Initiative, specifically under Action Plan 3 Focus Area 5.2. Okay, so our roadmap for the day is to cover technical team updates, hear a brief update from the checklist team, and then we'll go over the current study schedule and progress. So now that we're in production mode, we are using the following format for our technical team to provide updates to you all. We piloted this approach last quarter, and it seemed to work really well, so we're going to move forward with that. So our updates in the next section are bucketed into 3 categories. So our work that has been completed, work that is currently ongoing, and then updates on work that we plan to undertake within the next 3 months. And today we have updates from the weather generator team, the lake level team, and the wave and surge team. So with that, I'm going to pass it over to Dr. Scott Steinschneider from Cornell to give an update from the weather generator team.
Sure. Thanks, Caitlin. Hi, everyone. This is Scott Steinschneider at Cornell. So yeah, I want to give you just a very brief update on the work that we've been doing for the stochastic weather generator as a part of this project. So just as a quick reminder of sort of what this model is and what we're using it for, we're showing the basic schematic of that in this flow chart here. The weather generator is going to be the tool that we use to generate long sequences of daily weather across the entire Great Lakes Basin. And those sequences of weather are then going to be used as input into several other models that estimate runoff into the Great Lakes, precip on the Great Lakes, and evaporation off the Great Lakes, as well as ice conditions on the Great Lakes, which then flow down into routing and regulation model, ultimately to let us look at water levels on the Great Lakes. And so for this particular weather generator, there's really 2 major things that we use it for. The first is to generate a baseline scenario of weather across the entire Great Lakes Basin. And that's going to that'll set the baseline in terms of what current conditions are. And then we can generate a series of future climate change scenarios with this model, which can then be compared against that baseline. So if you go to the next slide, I'll now just sort of briefly share progress of what we've been doing and where we intend to go in the near-term future. So in terms of completed work, there's really 4 items that I would highlight here. The first is that we've been coordinating pretty closely with the water level modeling team, who will be presenting right after me, in terms of the final data sets that we should be using. So we have finalized that coordination process, and we have selected the final data sets here. So the important piece to highlight is that the data that we use to drive the weather generator needs to be and produce the exact data in the right format that the water level modeling team then needs to use for the conceptual runoff models and the evaporation models and the like. And so we've worked all that out, and we have the historical data sets of precipitation and temperature and solar radiation and the like that are necessary for the water level modeling team and that our stochastic weather generator will produce. In addition to that, we've done two major things in terms of model development. So that second bullet there identified weather regimes across the annual cycle for the Great Lakes Basin. Basically, the way that this model works, this stochastic weather generator works in a nutshell, it's sort of a two-stage model. In the first stage, we identify and simulate large-scale patterns of atmospheric flow in the atmosphere. Those are what I refer to as weather regimes. So we create a model for those. And then the second thing we do is once we have a model of the weather regimes, we then can simulate local weather, precip, and temp based on the weather regime we're in. So we have, in terms of completed work, we've identified and created a model for the large-scale atmospheric weather regimes that we want to use for the Great Lakes Basin. And so that is done. And then in addition, we've integrated the final data sets that we coordinated with the water level modeling team. We've integrated that into our model to generate the local weather. So that'll be that third bullet there. And we've just started to develop some test runs for that baseline scenario across watersheds throughout the Great Lakes. And that would be that last bullet under completed work. So having developed some initial test runs for the baseline scenario, in terms of what we're doing right now, so now moving to ongoing work, what we're really doing is we're assessing the skill of the weather generator in that baseline scenario for generating a slew of weather statistics across different temporal scales and spatial scales throughout the Great Lakes Basin. And then what we plan to do, what we can sort of continuing to do as we assess model skill, we see if there's any deficiencies in any particular statistics that we want to reproduce in this baseline scenario. And then we can adjust model calibration to refine those weather statistics under that baseline scenario. And so that's an iterative process, and that's what we've started to do now and are going to be working on in the near future. And then sort of once we finalize that process, moving on into the sort of medium range future, once we feel like the baseline scenario from the weather generator is performing really well across the entire Great Lakes Basin, then we would shift over into developing future climate change scenarios with that same model, which can then be compared against that baseline. So I'll leave it there and pass it off to the next group.
Thanks, Scott. Before we move on, I want to invite anyone with questions about the weather generator or the generation of the baseline scenarios to come off mute to ask any questions or pop something into the chat. Okay. I don't see anything in the chat,
Caitlin,
but...
Hey, Caitlin,
yep.
This is Scudder Mackey. Yep. You know, I can't not ask a question. Scott, could you talk a little bit more about the scale of these simulations? You know, because are they done on a lake by lake basis, or are they done across the entire basin? How is this sort of when you're modeling this weather? You know, I'm just a little bit more interested in the scaling of the work that you're doing.
Sure. So I'll try and answer that, commenting on the resolution of the data and then sort of how it's generated to maintain spatiotemporal consistency. So in terms of the resolution of the data, we are talking about daily data that is being generated for about 1,000 years or so. So it's a lot of stochastically generated data at a daily scale. And it's being generated for, well, I forget the number, but it's something like 120 or 150 watersheds that contribute runoff into the 5 Great Lakes, as well as time series of precip and temperature over each lake. And we also need to include some generation of data over the Ottawa River and downstream on the St. Lawrence, because some of that's important for modeling Lake Ontario management and water levels. Right. So that's the spatial scale and the temporal scale. In terms of how we generate it, we don't generate this data independently by lake. It's generated across the entire basin all in one go, because we need to maintain the spatiotemporal correlation across all the variables sort of through time and across space. So you can imagine, right, a storm moves over, dropping precip, first in the west and then moving over to the east, we got to sort of maintain that sort of progression in the simulation. And so the way that we do that, this is where the weather regime-based modeling comes in use. The weather regimes are basically these large-scale atmospheric centers. They are regional to continental in scale, and they sort of help us maintain the spatiotemporal consistency simulation over such a large region. So I'll leave it there, but basically the idea is to be sure to maintain correlations in space and time across all this stuff so that we don't break important relationships.
Okay, yep, thank you. That helps. It gives me a better feel for what you're doing. Thank you.
Great, thanks.
I actually have a question too. Keith Roberts from Baird. Scott, I just wanted to know how this feeds into the hydrodynamic modeling component. You mentioned that is ready to go with the water level modeling.
Yep. So in past presentations, we have shown a flow, like a larger scale flow chart. You can kind of see it in the bottom right-hand corner of the current slide that shows sort of all of the model components that we're working with. So this stochastic weather generator is producing these time series of precip and temp, which are going to drive our models of static lake levels. So this is going to be sort of like average lake level conditions across all of the 5 Great Lakes. The weather generator output is really driving models for those static lake levels. So this would include the LBRM, which is the runoff models for each of the Great Lakes, as well as the large lake thermodynamic model, which is sort of modeling ET off of the lakes. The output of the weather generator is driving all that stuff. What the weather generator is not driving, if you go to the, I think, previous slide, it might be helpful for me to answer this question. In that, if you squint in the bottom right-hand corner of this slide, on the right-hand side of that flowchart figure, you'll see a series of models there, which are wave and surge models, which are really require data at much finer resolution and over shorter duration. So like hourly type scale, storm scale things for wave and surge. We've separated these two, the static water levels and the wave and surge models, and then we have a probabilistic way to combine them at the end. So the thing I'm just trying to emphasize here is that stochastic weather generator output doesn't drive directly those wave and surge models. It's just driving the models for static lake levels. And then we have a strategy for this probabilistic combination of the output of those two sets of models to get at the full distribution of total water levels.
Okay, thank you for that answer.
Yep.
Okay. All right. Thank you, Scott. And now I'm going to shift over to Dr. Lauren Fry for the update from the water level modeling team.
Okay, thanks. Yep, so I'm Lauren Fry. I'm a research scientist at NOAA's Great Lakes Environmental Research Laboratory in Ann Arbor. But the work I'm talking about here is really done with our partners in Army Corps of Engineers in the Detroit District Office and academic partners at the University of Michigan Cooperative Institute for Great Lakes Research. So Scott kind of walked through a little bit here, but I'll go through it again just to show how we're taking that weather generator output for the static lake levels, which I might also refer to as lake-wide average water levels. So we're taking that weather generator output. We can use the precipitation directly, the precipitation over the lake directly. We propagate the weather generator output to runoff into the lake using the large basin runoff model, which is a lumped conceptual model that we've reconfigured to address concerns from earlier studies related to overestimation of evapotranspiration. I'll talk more about that in a little bit. And then on the overlake evaporation side, we're using the large lake thermodynamic model, which is a one-dimensional, simple lake thermodynamic model to compute evaporation. As we're computing evaporation, we're also computing percent ice cover, which is also being used in the later modeling efforts by the wave and surge team. So those are those top three boxes in the red box, the top three blue boxes: runoff, precipitation, and evaporation. That's what we combine together to get our net basin supply. We're routing that net basin supply through regulation and routing models that incorporate lake-to-lake relationships and regulation rules and logic for Superior outflow and Lake Ontario outflow. And so from that, we'll get a set of water levels for the baseline condition that we get from Scott, and also the various climate change scenarios that we get from Scott. So a distribution for each scenario. In addition to that, we have these two green boxes in the lower left part of that red box. And those are what we've been calling our check modeling approach for checking at the runoff component. And I guess the reason that we're doing this, we're running another set of models to check our runoff, is because in order to produce the really large data set that we need using the weather generator, we need a really quick, computationally efficient set of models. We know that there's potential pitfalls of using computationally efficient conceptual models. One being the evaporation approximation that's been identified earlier that we're addressing with a new configuration of evaporation, but the other being just simplifying things so much that you're relying too heavily on a calibrated model, and that may not be representative in an alternate climate regime. And so we're running a more physics-based model, a distributed model called WRF Hydro. Our partners at the Cooperative Institute for Great Lakes Research are going to be leading that effort to run a handful of the scenarios and the baseline condition to help us understand the biases and complexities that we may not see in the output from the conceptual model. Okay, next slide. So I'll go into the completed work. I mentioned this new configuration in the large basin runoff model for estimating evapotranspiration. So earlier versions of the large basin runoff model were known to overestimate evapotranspiration, causing dramatic reductions in runoff into the lakes. We've worked to incorporate a routine that is less sensitive to temperature changes and is a closer approximation to an energy balance approach that has been advocated for. And so we've encoded a Priestley-Taylor approach to estimate evapotranspiration in the large basin runoff model. So that's done. That configuration required another set of input variables. We needed to incorporate net radiation into our data set. And so we worked to identify an appropriate data set to build that, or appropriate gridded data set to build that from. We selected the data from Livni et al, and we've processed that to subbasin averages for subsequent use by LBRMPT. In addition, we've worked to build a workflow for modeling the lake levels that incorporates computing runoff, evaporation, getting the precipitation, computing net basin supply from that, and directing it through the regulation and routing model. We developed a workflow that would be efficient enough to be able to run many, many long simulations. And so that's effort that's been completed. And then the last item in the completed work is that we're excited that we've advertised a new postdoc position to work on that WRF hydro modeling that I talked about with the check model. And I'll talk a little bit further in the next slide. But there's a postdoc announcement out there. I have a link on the next slide, and SIGLR, our cooperative institute, is just getting into the work phase of their effort. So that brings us to the ongoing work for water levels. For the LBRMPT, because we've established a new evaporation estimate in there, we need to recalibrate it. And so we've been looking into alternative, more state-of-the-art calibration approaches that have been used in the past. And we are working on testing that configuration with the new evapotranspiration routine and net radiation data. So once we've established what the calibration method that we want to use, then our next step will be to run through calibration, and we can really begin baseline simulations using the weather generator output. Next slide. Okay, so along with that simple conceptual modeling work that I've described more in detail, I also mentioned the check models, which are those green boxes there. What I didn't mention when I was going through the data diagram earlier is that we also have a similar check model approach that we're using to evaluate the large lake thermodynamic model output for evaporation and ice cover. So those are those green boxes that kind of show up in the middle right of the screen. So that both of those efforts are being led by our Cooperative Institute for Great Lakes Research, and that will begin by identifying appropriate gridded forcings that can be used to drive those models. They're distributed models, and so we can't just take the lumped forcings that we're getting from the weather generator, and we want our forcings to be as consistent as possible with what we get for the baseline and climate change scenarios. So that'll be kind of the first big effort. And then simulation will begin with WRF Hydro. That's going to be led by Dr. Drew Grunwald at University of Michigan, and the ice cover and evaporation will be modeled by Ayumi Fujisaki Maname at the Cooperative Institute for Great Lakes Research. And then once they have a set of simulations for a subset of those climate scenarios that we get, then we can start evaluating some of the biases that we might see between the simple conceptual model and the more computationally complex models. So ongoing work there is recruiting the hydrology postdoc that I mentioned. And I'm sure we can get you this link somehow if you know a good candidate that you'd like to refer. And that the first job of that person will be to work with Drew and Ayumi to identify appropriate gridded forcings that we need to use for driving WRF Hydro and FECOM. And so that's the overview of the water level modeling work that I have here.
Thanks, Lauren. And I can include this link in the follow-up meeting material. So we can get that out to everyone for sure, the live link. Okay, any questions for Lauren and the water level team? I didn't see anything come through the chat yet, but I'll give folks an opportunity now to come off mute if they want to. And yeah, and I'll go back a slide, yeah, just to the ongoing work to help jog people's memory if they have questions. Okay. Okay, not hearing anything. Oh, thanks so much, Lauren and team. Okay. So next, I'm gonna pass it over to Dr. Chris Massey with ERDIC CHL for an update from the Wave and Surge team.
Hey, thanks, Caitlin. I appreciate it. Just want to do a quick mic check, make sure you can hear me okay.
Yes, thanks.
All right, thank you. And thank you for the thumbs up, John. I appreciate that. So I'm Chris Matz with the Army Corps of Engineers at the ERDIC Engineer Research and Development Center's Coastal and Hydraulics Lab. And myself and Bob Jensen and Margaret Owensby here leading the wave and surge modeling within the lakes. Dr. Norberto Nadal and his team will be looking at the statistics of the wave and surge results that come out of those. And so I want to dive just a little bit deeper into the complexity of these models. These are going to be lake level models or lake specific models. So each lake will be modeled coming in with this. And we'll be looking at not only the storm events, where we're looking at about 180 historical storms coming into the area, but we'll be combining those with the historical ice coverages as well as future potential ice coverages coming out of the larger scale modeling and the climate scale modeling that Scott and Lauren were talking about earlier, as well as varying the starting water levels or the static levels of the lake-wide lake averages that will be used for the different wave and surge modeling initializations that are done. So if you'll go ahead, Caitlin, and advance the slide, please. And so this just kind of gives you an idea of some of the work that we've already completed, ongoing and next steps. So one of the things we've decided, and we've talked about in some previous meetings, was to include summer storms in the list of storms. Basically, we're using the FEMA flood risk map studies that were done a few years ago as a starting point for our analysis and work, and extending that. In that work, the summer storms were left out, and that was because in general, the strongest storms in the lakes were occurring during the winter time, and so the summer storms were left out. However, it's in the summertime that the static lake levels are actually at their highest, so it's possible that you could still have some significant flood events during the summer. And so in order to characterize and capture the flood hazards across the seasons, we're going to be adding back in some summer storms for that. We've decided to use a coupled AdCirc-SWAN model. So the AdCirc is giving us the two-dimensional depth average circulation and water level surge, and then it is tightly coupled with the SWAN, unstructured SWAN model, which is going to give us wave height, period, and direction. And those two models are coupled, meaning that they share information dynamically during the course of the simulation. And that's very important because, as you know, waves are depth limited, and so as the surge or the water levels are changing and moving, the wave heights can change with those as well. And then, of course, the wave conditions are affecting the circulation. You can have wave-driven currents, and so capturing those are important in that dynamic scenario with that. We've also identified a consistent set of ice concentration map files for the time period from 1973 to 2019. We've got a reference down there for that. And so those are going to be a data source for us as we look at those historical ice maps and helping construct the ice map fields that we'll be using for the simulations. Ongoing work that we're currently doing right now, we're still evaluating the storm suites, starting with Lake Ontario as the first lake we chose to start with due to availability of data. So Dr. Norberto Nadal and his team are going back and examining the work that they did back in roughly the 2012 timeframe for the FEMA, and some of their extended techniques since then, and making sure that we've captured the storms that were used previously, as well as storms that have occurred since that 2012 timeframe and the summer events. So coming in with our methodologies for those. And like I said, we're anticipating about 180 storm events per lake as we go over. And of course, there will be storm events will overlap between those. We are creating brand new AdCirc-SWAN model domains, meshes for all the lakes, beginning with Lake Ontario, and so that work on the Lake Ontario mesh is well underway. We're using the FEMA meshes that were developed previously as a gut check and as a guide. looking at the resolutions between the models and making sure we're capturing events, or not events, but locations that were of significant interest in the original FEMA modeling, and then extending that as we go forward. We'll be using some new software that was developed recently by Dr. Keith Roberts and William Pringle coming out of Notre Dame. This is the Ocean Mesh 2D software. We'll be using those to allow us to generate these very accurate meshes that allow us to concentrate our resolution in the nearshore areas to capture some of the effects that are very important there. And that's where a lot of our projects that we'll be looking at are of interest. Wetland restorations, habitat restorations, and so forth, beach, dunes, moving forward with that. We're in the process right now of also preparing boundary shape files for Lake Superior, which will be the next lake that we'll begin working on after Ontario, and doing that, as well as we've started working with our Jobeltech lab to start collecting and synthesizing together the DEM data for all the lakes. They're working in that independently with a girl group here, and helping us just to pull it all together for our needs for interpolations for these as well. In the coming months, we will also be creating and sharing with the stakeholders and others these ideas of these save point locations. These will be point locations within each of the lakes where very high resolution time series data will be collected, as well as where the statistics for annual exceedance probabilities of water levels and wave heights will be calculated and computed and made available. And so what we want to do, we want to make sure that our stakeholders have buy-in to say, hey, this area is kind of important to us. Let's make sure we've got a significant number of points here to capture that for our needs. Because the idea now with these is that with the data that we'll be producing coming out of this, it will feed into a variety of uses and needs, and I'm going to go into that a little bit more in the next slide. So we want to make sure we get good feedback with our partners on this. We're also be looking at testing methodologies for extraction and conditioning the mean daily ice concentration fields from each lake, using mean daily ice concentration maps and base simulations for those, and then generating these basically binary ice maps for use of ice, no ice locations, in terms of also thinking about future conditions for that as well. Next slide, if you will, please, Caitlin. So there's some very good news in the sense that with the wave and surge modeling deliverables that we have initially, in the scope that we had, what we were going to be able to deliver were equivalent to a deep water wave zone. Really, we would be stopping in terms of our data, being able to deliver that in the deeper water. Now, using the AdCirc SWAN, we'll be able to propagate that all the way into the inland inundation zones with that. And in addition to that, we'll be able to consider doing this wave and surge modeling on the full range of, not a full range, but a broad range of future climate scenarios for these. So this will be where we'll be able to now look at different initial static lake levels and run a storm over those, with these different initial starting points. This will allow us to capture nonlinear effects, which are very important, particularly in these nearshore areas where our projects and areas of interest typically are. As well as being able to bring in these different ice concentration maps. And so per climate scenario that we'll be looking at, and so with some additional funding that was secured, we'll be able to come in, instead of just doing one base level of set of simulations, we'll now be able to do an additional 9 simulations to come in to really fill in that probability space and to consider more of these per climate scenarios with those. And then being able to use these new meshes we're creating with these new technologies, we're also being able to concentrate our data and bring it out of the deep water zone into the near shore zone. And really what that means is that in a lot of cases, the data that individuals will need to evaluate a project as viability, or what the current conditions are, survivability, those kinds of things, that data may already be there now. when this modeling is complete and the statistics are computed, it would not require an engineer or a technician to pick up and run additional models to move that data from the offshore into that nearshore zone. So we will be able to take this a step further to reduce the potential for additional work in the future. That doesn't mean we're going to eliminate everything. Additional models will be needed. If you're looking at specific project impacts, maybe will be that. The other important part to mention is this is what we and FEMA would refer to as a still water level modeling that comes out of the ADCIRC-SWAN combination. So it has wave effects in it, but it does not have wave run up and overtopping. Those are specific terms in there that are relating to that, and that would still require some additional modeling. We will have inundation, so we will have water coming out of the lake up onto the land as appropriate, force from these storms. So I don't want to give that impression, but there's very specific term to wave overtopping. If you can think about being at the beach and you're watching those individual waves breaking and that water kind of sloshing up and over something, that's what we're meaning by modeling those individual wave trains. That's not what we're doing. So with this new funding, we're able to do these new meshes. We're able to extend this modeling and consider more of these climate scenarios. So these are really big win-win-wins for both present day and future conditions as we look at these project levels. Next slide, please, Caitlin. In addition to this, the data that is being produced, the time series at these save points and the statistics, these annual exceedance probabilities, this data will be incorporated into what is known as a coastal hazard system, which is a database and visualization. You're seeing some screen grab images here for those. There's an existing data set for the Great Lakes that came out of the FEMA study back in the 2012 time period. So this will be an addendum to that. We'll be adding and refreshing the data that's there. The older data would still be available. But this new modeling, these new statistics calculations will now be in place. And as you can see, you could come into a particular area and zoom in, and there would be these save points, and you could select a save point, and then once you've done that, you might end up with a curve, looking at a curve like you see in the bottom right-hand corner. This is your still water level for a given location. That's the black line is your best estimate to those water levels with those annual exceedance frequencies down at the bottom. And then the height of that water level moving along the y-axis here. And then the blue region is your confidence interval. Your 80% confidence interval in this case gives you an idea of error margins and so forth. And so for a lot of engineering needs and design and just general information, this kind of information alone is sufficient. And then for other areas, for project designs and so forth, this information would actually be a starting place. And so having all of this already available for our engineers and our partners out there really saves them a lot of front-end legwork. It gives very high quality data and statistics coming into these. And so this website will be publicly available. It already is. You could do a web search on it right now. You can see the address at the top. And so this will be a way of disseminating this information, and we're really, really excited to be able to extend that with these new future climate scenarios as well. So those are the updates for the wave and surge. So Caitlin, I'll turn it back over to you.
Thanks, Chris. Okay. I did not see any questions come into the chat, but I will pause and see if anyone has a question and wants to come off of mute.
Hey, Caitlin, this is Scott again. Really appreciate the effort. I know we had in some of the prior meetings discussions, and there were concerns about, you're producing a set of, deep water wave statistics. And I really appreciate the effort to move this into the, shallow water waves into the nearshore zone. That's going to make your product much more useful to us. One of the things I'm interested in, and we, I happen to be in Ohio, and we deal with Lake Erie, and we are subject to some substantial sesh events. The short-term elevation changes in water that are driven by storms. And I know there was some concern about whether or not you folks may be able to handle that. I think you're getting closer here, and I think you had mentioned something about, we're doing still water, it's basically still water elevations. And so wave run up and some of that is not incorporated, and I understand that. I'm wondering, you said that changes in still water elevations as a function of storms coming through. Is that a way that you may be able to start to simulate the potential of these shorter 12-hour, 16-hour sesh events? I'm just curious about this, the resolution. I'm trying to, scaling resolution. I had a discussion, the question for Scott earlier on this. Maybe you could help clarify that a little bit.
Sure, Scott, that's a really good question, and that's something we're specifically going to look at. What we would like to do is identify some known SAIS events in the lakes, so that we can, go in and specifically look to see if we're able to be capturing those. The big piece of whether we're able to capture that is in my mind, not so much the wave and surge model itself, but the meteorological products that we're using to force that data with. The scale, the time frequency, and so forth of the historical wind and pressure fields that we're using. If those are of sufficient accuracy with those, we should be able to capture at least some of the response from these SAISs with that. But what we'd like to do is get your help and others' help in identifying maybe a couple of events where we know for sure SAISing was going on, so that we can tune in and really see and answer that question definitively. Yes, we're able to capture that with our existing wind and pressure fields in combination with these models, or this is still an area that we're missing that. So that's definitely an area that we want to answer that question for you.
Yeah, that's going to be, I think, looking forward to that discussion, because I'm thinking about, if you're looking at still water elevation, if you're looking at a whole lake view, that's one thing. But on one side, there have been such events here where we've had a 16-foot difference in the water surface elevation between Buffalo and Toledo. And that's not insignificant. And if you're talking about, we're talking about inundation on one side, but we're also talking about, substantial drawdowns on the other side. And that has, depending on the timing of those, significant impact on the types of projects that potentially we're trying to engineer our designs for and design for. Now, these are short-term excursions, but still, this is something that it would be worth having a discussion on, because we're in the middle of right now of working with a design team for a number of projects on the western side of the state. And we are concerned about these SESH events, and because it is significant in terms of how we modify our designs and how we account for those short-term fluctuations in water levels. So thank you very much. I don't want to take more time here, but let's have a further discussion on this. I think it's going to be useful.
Absolutely, and thank you for that. And for the general audience too, I want to just clarify again, when we talk about a still water level, that does not mean it's a static flat level. That's what the model starts with. But when the models are running, they are responding to the winds and the pressures and so forth, Coriolis effects and everything. And so you do get a difference in water levels across the lake. That water is in fact moving. It's just a term that's used to really mean that it does not have wave run up and overtopping in it when we say still lake levels. And so those drawdowns that you're talking about, we've seen that in the models, and we will capture those kinds of events as well. So just a clarification on that. But absolutely, Scudder, I'd love to have these further conversations with you and maybe get your help in identifying some specific time periods where you've got data and seen conclusively with these SAGEs. Thank you, sir.
Yep.
Okay, additional questions for Chris and team?
Good afternoon. I had a question about the your calibration and the wave energy that your model is working off of. Are you not including compensating for the anthropogenic sources of wave energy, like the commerce ships that come through and stuff like that?
That would be too fine of a scale, I think, to be putting in those vessel effects into these models.
Okay, thank you.
Yes, sir. Thank you.
Okay. I don't think I see any additional hands, but last call. Okay. Well, thank you so much, Chris. I appreciate it.
Yep, thank you.
Okay. And next, we're going to move into a brief update on the design checklist team. And Jim, if you are on the line, I'm going to pass it over to you.
Yep, on the line. Not much to update here. We're putting the checklist together. It's probably, I don't know, second or third time you've heard me talk about this. We put a team together. We had our first kind of a kickoff meeting, and we were soliciting input, and so we're still soliciting input. So probably this fall we'll have another meeting, and then we'll start I don't know, identifying the types of things that we want in this checklist. Really, the things that the info we're looking for are the types of projects you would want checklists for. So if you're building a coastal wetland or a fish reef, the types of things you're envisioning needing a like an engineering design checklist for. And I know this is going to vary from state to state, and I suspect the guidance may even vary from state to state, since the rules are different and just approaches are different in the different states. So, so yeah, that's about it. Keep your ears open for our next meeting, and if you've got ideas you want to send me ahead of time, feel free to do that.
Thanks, Jim. Okay. Moving on. So our final topic for this afternoon is an update on the study schedule. Okay, so we have our current schedule up here, and you can see where we are currently located by the orange arrow here. So we're in June of FY22. And as you heard today, we are heavily in production mode now from the weather generator team, the lake level team, and the wave and surge team. We have updated this schedule to incorporate those new developments that Chris mentioned in terms of the ability to do additional simulations and to build out and host our information on the coastal hazard system. So those are now reflected here in the schedule and will be moving forward. And I also did want to highlight for the wave and surge, you can see that we are anticipating working on those in a sequential order, and we have things laid out this way because we are going to be leveraging the most recent JABLTEX LiDAR. So we kind of have to follow the order of in which the data is being processed. So as Chris mentioned, they're currently working on Lake Ontario, and next, and I think, Chris, I think you're already starting to work on Lake Superior as well, but just wanted to kind of explain the order here and how we're looking to roll things out. Okay, I think that's all I wanted to cover here on the schedule. And yeah, as we have been doing, we will keep updating this and keeping you apprised of any major changes or updates that happen here. And with that, I think I will bring things to a close. Don't see any additional questions that have come into the chat. Our next meeting will be September 22nd, and you all should have that meeting invite already. And we will be distributing meeting materials in advance of the meeting. And then as a follow-up, I did make a couple of notes on do-outs. I will send the CGLR job advertisement that Lauren mentioned in my follow-up email. And then I will also include a short snippet from what Jim mentioned for the design checklist team, the topics that they are looking for input from you all on. And then, as usual, I will also include a link to this video, so if you have any colleagues that weren't able to participate today, they'll be able to check out the YouTube video at their leisure. So with that, thank you so much for your participation this afternoon. Thank you to the members from our technical team, and we will talk again in September. Thanks, everyone. Take care.
Thanks. Bye-bye.
Bye.